Problem number 2 in particle and continuum mechanics practice final exam. So we have a bead of mass m slides without friction on a circular hoop of radius r. The hoop rotates about its vertical diameter with constant angular speed, capital omega. Let theta be the angle from the downward vertical. Okay, part A, write the Lagrangian. Part B, derive the equation of motion. Part C, find all the equilibrium points. And part D, determine their stability as a function of capital omega. Okay, so this is Lagrange formalism with constraints problem. So part A, Lagrangian, we say that the bead has two contributions to its speed. V squared equals r squared theta dot squared plus r squared omega squared sine squared theta. So the kinetic energy is going to be T equals 1/2 m r squared theta dot squared plus 1/2 m r squared omega squared sine squared theta. And since theta is measured from the downward vertical, the height above the bottom is going to be h equals r times the quantity 1 minus cosine theta. So the gravitational potential energy is going to be V equals mgr times the quantity 1 minus cosine theta. And going ahead and dropping the irrelevant constant mgr, V equals negative mgr cosine theta may be used also. So we could let L equal T minus V, and using V equals negative mgr cosine theta, L is going to equal 1/2 m r squared theta dot squared plus 1/2 m r squared omega squared sine squared theta plus mgr cosine theta. Okay, so that is part A. Part B, we want to derive the equation of motion. So for the equations of motion here, we have the following. Equations of motion, partial derivative of L with respect to theta dot equals mr squared theta dot. And so d dt, partial derivative of L with respect to theta dot equals mr squared theta double dot. And then our partial derivative of L with respect to theta equals mr squared omega squared sine theta cosine theta minus mgr sine theta. And the Euler-Lagrange equation is mr squared theta double dot minus the quantity mr squared omega squared sine theta cosine theta minus mgr sine theta, and that's equal to 0. So mr squared theta dot double dot equals mr squared omega squared sine theta cosine theta minus mgr sine theta. So going ahead here and dividing by mr squared, theta double dot equals sine of theta times the quantity omega squared cosine theta minus g of r, and theta double dot plus g over r sine theta minus omega squared sine theta cosine theta equals 0. So that's part B. Moving along now to part C, the equilibrium points. So equilibrium requires theta dot equals 0 and theta double dot equals 0. So sine of theta times the quantity omega squared cosine theta minus g over r, that has to equal 0. So therefore either sine of theta equals 0 and either theta equals 0 or 0 comma pi. Okay, so from here we could say or omega squared cosine theta equals g over r, and cosine of theta equals g over r omega squared. So the pair off bottom equilibria exists only if we have the following: g over r omega squared is less than or equal to 1. So omega squared is going to be greater than or equal to g over r. So the non-trivial equilibria are theta equals plus or minus inverse cosine of g over r omega squared, or equivalently on the hoop, theta is going to equal inverse cosine of g over r omega squared, and theta could also equal this 2 pi minus inverse cosine g over r omega squared. Okay, so that's part C, and now for part D we go into the stability analysis here. So equation of motion, theta double dot equals f of theta, where f of theta equals sine of theta, omega squared cosine theta minus g over r. So for a small perturbation, theta equals theta naught plus eta, then eta double dot equals f prime of theta naught eta. Okay, so building on this, what we'll say here is small stable oscillations are going to require f prime of theta naught be less than 0, and f prime of theta here, that's going to equal cosine theta, omega squared cosine theta minus g over r minus omega squared sine squared theta. So stability conditions, so stability now of, we'll start with theta equals 0. At theta equals 0, sine of 0 equals 0, cosine of 0 equals 1. So f prime of 0 equals omega squared minus g over r. Thus, theta equals 0 is stable when f prime of 0 is less than 0. And therefore, theta equals 0 is stable if omega squared is less than g over r. And it is unstable if omega squared is greater than g over r. And at the critical value, omega squared equals g over r. The bottom equilibrium loses linear stability. Okay, now moving on to the stability of theta equals pi. At theta equals pi, sine of pi equals 0, cosine of pi equals -1. So f prime of pi equals -1 times this quantity, negative omega squared minus g over r, and that equals omega squared plus g over r. And since f prime of pi is greater than 0, theta equals pi is always going to be unstable. And the stability of the off-bottom equilibria for the non-trivial equilibria, cosine theta naught equals g over r omega squared. And at these points, omega squared cosine theta naught minus g over r equals 0. So f prime of theta naught equals negative omega squared sine squared theta naught. And since negative omega squared sine squared theta naught is less than 0, for non-zero sine theta naught, the off-bottom equilibria are stable. So theta equals plus or minus inverse cosine of g over r omega squared are stable if omega squared is greater than g over r. And at the critical point, omega squared equals g over r. They merge with theta equals 0. Okay, so that's problem number 2. Thank you very much and have a great day.